we continue with the topic of modeling these complex atmospheres, and the next talk by Diana Powell from UC Santa Cruz about the modeling of particle distribution in clouds.
Great, thank you so much. So today I'll be discussing cloud formation in the atmospheres of brown dwarfs and hot Jupiters. And this is work that I've done with one of my thesis advisors, Xi Zhang, as well as Peter Gao, Mark Marley, Jonathan Fortney, and Vivienne Parmentier. So clouds, as we've already heard, are seemingly ubiquitous in the atmospheres of extrasolar objects. And these clouds play important roles in regulating radiative transfer and chemistry. So clouds also interfere significantly with observations. Clouds are commonly inferred through the lack of atmospheric spectral features, consistent with the presence of an optically thick absorber. For example, here in the top left, I am showing the featureless transmission spectra of the super-Earth GJ1214b. Furthermore, clouds also likely contribute to observed spectral variability, either due to inhomogeneous cloud cover, climate cycles, or both. So here shown in the bottom left are the faintest and brightest spectra of a variable brown dwarf. And finally, we may have observed the presence of clouds directly in the atmospheres of several brown dwarfs via a broad silicate absorption feature in the mid-infrared, as shown in the spectrum on the right. So we approach the study of clouds from a microphysical perspective, using the community aerosol and radiation model for atmospheres, known as CARMA. So CARMA is a well-tested code that has been applied to nearly every body with an appreciable atmosphere in our solar system. CARMA works on an Eulerian grid of particle size and altitude, where particles are allowed to grow and move into a larger bin or evaporate and to move into smaller bins. Particles can also move vertically along this grid. So CARMA is a particularly useful tool because it allows us to fully resolve cloud particle size distributions from first principles in a time-dependent framework. So on the right here is a general picture of how CARMA operates. Here I'm showing altitude in the atmosphere, as well as temperature and pressure. So condensable gases are mixed from a reservoir in the deep atmosphere until they reach a point where the gases become supersaturated and clouds can form via microphysical processes. These particles can then themselves be vertically mixed or settle gravitationally. So now let's take a moment to zoom in on the microphysics in particular. So CARMA treats three microphysical processes. There is nucleation, which can occur when the background gases are supersaturated and nucleate on small seed particles. Homogeneous nucleation can also occur, and the background gases can nucleate without the presence of a seed. There is also condensation, where the condensable gas species diffuse through the atmosphere until they reach a cloud particle and condense. And finally, there's coagulation, where two cloud particles can collide and stick, forming either a new spherical particle or an aggregate. So as an introduction to CARMA, I will briefly make two comments about our work on hot Jupiters. However, I will have very little time to discuss this aspect of our work, but we have a lot of exciting results, so if you're interested, please find our recent paper. I will then spend more time discussing our more recent work on brown dwarfs. So here's a primer of what results with CARMA look like, here for the case of a hot Jupiter. So the x-axis is particle radius, and the y-axis is atmospheric pressure, with higher pressures indicating lower depths. And I will be plotting the mass density of clouds. In this setup, I am simulating the formation of just two cloud species. First, a population of silicate clouds form, and then a population of titanium clouds form, and then a population of silicate clouds form. As you can see, the titanium cloud base is lower in the atmosphere than the silicate cloud base. The titanium population grows until it is nested below and next to the population of relatively large silicate cloud particles. So our models tend to eventually reach a steady state as there's periodic nature which may be real, like the climate cycles on Earth. However, for the rest of this talk, I will be presenting time average solutions. So one of the most powerful features of the CARMA code is that it allows us to derive fully resolved cloud particle size distributions from first principles. So when full transmission spectra are calculated, here for the case of a hot Jupiter, the need for this resolution is clear. So here the black line shows the resultant spectrum considering the fully resolved size distribution, while the blue line is the spectra assuming the same amount of cloud mass is present in one mean particle size that can only vary as a function of height. As you can see, there is a difference in both shape and amplitude between the two spectra. Okay, now let's transition to brown dwarfs. So on the left here, I'm showing a color magnitude diagram. In gray, I've highlighted the standard sequence of M and L-type dwarfs. And now in red, I'm highlighting a more recently discovered sequence of very low gravity objects, which is distinct and redder than the sequence for field objects. So here, we will be showing preliminary results for cloud properties of these objects. The initial sample of our grid ranges in equilibrium temperature from 1100 to 1600 Kelvin. And the new Sonora pressure temperature profiles for these objects are shown here. All of these models have a low, while still physical, log G of 4. And these equilibrium temperatures allow for the condensation of several different cloud species, as shown and labeled in the dashed and colored condensation curves. When we calculate emission spectra for the very low gravity objects, shown here for the case of 1100 Kelvin object, we find that our cloud opacities result in spectra that, while not completely featureless, are distinctly flattened compared to the clear case. We have not yet rigorously compared these results to observations, but by eye, these spectra seem to be overly flattened. However, as I will discuss at the end of this talk, this may not in itself be reason for concern. So now let's place our models on the color magnitude diagram. On this color magnitude diagram, the very low gravity sequence is roughly highlighted in yellow. So the very low gravity profiles with clear atmospheres lie in this region of the diagram. If we now model these same profiles with Ackermann and Marley clouds, they lie here and are much redder, although they appear to start to become more clear at lower temperatures. When we instead consider karma clouds, those points lie here. And we can see a distinct shift toward the red region of the diagram, particularly for cooler objects. So something that is particularly encouraging about the karma results here are that the points follow the straight slope of the sequence down to the reddest regions where we are currently discovering objects, instead of curving off to the blue. So while the karma points here are quite red, these initial results, without any tuning, naturally reproduce the trend and rough locations of the very low gravity sequence given physical brown dwarf parameters. So now you might be wondering what makes these cloud models different. One major difference between the two model frameworks are the cloud particle size distributions. So here in color, I'm showing the karma cloud particle size distributions as a function of height, and in the dashed black line, I'm showing a representative Ackermann and Marley cloud particle size distribution for the same brown dwarf. So the karma distributions derived from first principles are not log normal and are generally not smooth functions. Also, if you look at the size distributions as a function of altitude, they vary in a manner that is difficult to predict a priori. So these distributions are not easily described by a reduced set of parameters. This difference in particle size distribution gives rise to different resulting spectra. There is, of course, also scatter present in the color magnitude diagram. And one fundamental property that can create the scatter is gravity. It is therefore illuminating to further compare our cloud model to the Ackermann and Marley cloud model for specific field brown dwarfs. So we do so here for the object from Mark's talk, 2M2224. This object lies roughly in the circle marked here. And now here again are the different models for this object. So we find that this brown dwarf lies roughly on the line connecting the karma cloud model to the Ackermann and Marley model. And we take this as confirmation that karma is moving in the correct direction. However, there's still work to be done in order to conclusively validate this model with observations. The next physics that we'll add to this model we expect will move these points more towards the blue. So before we move on, let's briefly examine the differences between standard field brown dwarfs and very low gravity objects. So here again, I'm plotting condensed mass density as a function of both particle size and atmospheric pressure. On the left is the resultant cloud particle distribution for a brown dwarf with a canonical log G of 5, while on the right is a distribution for a very low gravity object with a log G of 4. So both of these objects have the same equilibrium temperature. Here, the white dashed line indicates where the clouds become opaque in the J-band. And what is immediately obvious is that clouds in the very low gravity objects form and become opaque higher in the atmosphere. Another property that can contribute to the scatter seen in the color magnitude diagram is 3D cloud structure. So if these objects do indeed exhibit patchy 3D cloud structure, then the addition of some clear regions will likely shift these colors towards the blue. So here I'm showing a color magnitude diagram from Marley et al. 2010, where they investigate the impact of patchy clouds on an object's color. Starting from the cloudy objects in red, they increase the percentage of cloud cover in these green patchy regions until they reach the clear blue region of the CMD. They therefore find that heterogeneous cloud cover can significantly alter an object's location in this phase space. And it is therefore encouraging that our initial karma models lie to the redder regions of the CMD. So there are two important pieces of physics that our current models do not yet incorporate. The first of which is that in reality, cloud structures are likely 3D, which could result in a spectrum that is a linear combination of both cloudy and clear. From a dynamics perspective, it is really hard to imagine a convective atmosphere that is completely covered by clouds. So this is not yet something that karma can handle self-consistently. Furthermore, we are in the process of implementing self-consistent cloud radiative feedback, which will change the temperature profile and may therefore alter cloud properties. So looking forward, there are many things that we as a community can do to better constrain clouds. I'm particularly excited for the future of work in 3D studies, broad wavelength observations, direct imaging and polarization observations, as well as very necessary laboratory experiments. So thank you so much for your attention, and I'll leave you with my conclusions.
Thank you very much. Very interesting. Start here.
Jackie Faraday, American Museum of Natural History. And this comment on the preliminary results suggest that you can reproduce the very low gravity brown dwarf sequence that looks nice in the J versus J minus K, but of course we have much more info. The color magnitude diagram is really interesting, and say if you go to mid-infrared. So have you looked, how do you do it different and on different color magnitude diagrams, say?
So these results are quite preliminary. We don't know yet, but that's work that we're doing now. Actually, the models are running, so.
All right, next.
Adam Burkester, UC San Diego. This is fantastic work. It's really quite incredible results you're getting. I had a question on the details. When you're, have you incorporated sort of the optical opacity from the solid state features in the grains themselves to look at this sort of silicate grain feature in the mid-infrared?
I have not yet. Upcoming.
I have a question. So in your distribution of particle sizes with the pressure, you have this complicated function. Can you comment that is it somehow similar to gamma distribution typically used or some other distribution?
So I haven't compared directly to distributions just yet. In the future, I'd love to find some more simple parameterization that encapsulates this, but there are some interesting things about the size distributions that correlate to formation modes. So sometimes you have a nucleation mode or a growth mode. I think there's a lot of interesting work to be done.
Yeah, that would be very useful also for modeling, for direct modeling, like to put some contributions and see what's the effect, yeah?
Absolutely.
Thank you. All right, let's thank Diane again, and we switch to another talk.